So now that I've done a brief recap of what a memoizer is and kind of talked at a high level of how we're going to apply FutureTask to define our memoizer, let's go ahead and take a look and see how we can apply FutureTask to implement the memoizer. So this is going to go into the internal details. And again, you've heard about a memoizer several times here, so the concept should be old hat, but the implementation will likely be very interesting. So we're going to use a FutureTask to implement our memoizer. And the reason we're going to do this is to ensure that a computation for any long-running computation for a key that is not yet in the map will only run once, no matter how many threads simultaneously try to get access to that particular key and value pair at the same time. So here's the Memoizer interface. As you can see, it's Java code. You can get the Java code in my link at the bottom of the slide in my GitHub repository. It implements function, as we mentioned before, so that we can use a memoizer anywhere we expect to use a function. And I'll show you when we get to the application example in the next part of this lesson exactly how that works. We're going to have a field that will be a concurrent map, which will be implemented as concurrent hash map. And this map will ultimately associate a key of type K, which is generic, with a future to a value v that's produced by a function. And it's very important to remember that it's a future. And you'll see why we use a future here in a second. We use a future to ensure that this long-running function is only called one time. We don't want it to be called multiple times. And the future is exactly the thing that we need to make all this work. Here's the long-running function, or potentially long-running function, that's used to produce a value based on a key. And then finally, we have the constructor for Memoizer, and all it does is just stashes away the function, and we'll then use that when we need it in order to do the long-running computation. So that's basically kind of the fields and the constructor. Now let's take a look at the fun part. This is the apply method. So the apply method, if you recall, is the way in which a function does its thing. And what apply does is it takes a key and will then go ahead and return the value that's associated with the key in our Memoizer cache. And there's a couple of different cases to consider. So the first thing we're going to do is we're going to come along and we're going to say, hey, cache. Remember, it's a concurrent hash map. Try to see if there's already a value associated with this key. All right. Well, remember what we've got here is we've got this a map that's mapping keys to futures. And keep in mind, from the use case that could certainly happen, multiple threads could be simultaneously calling the apply method, which will then simultaneously call the get method for the same key that doesn't yet exist in the map. So that's the scenario that we're most interested in. If there already is a value for this thing, we're done, right? We just get back the future and we get its result and we're finished. But the interesting case is the first time in case. Now, what's important to remember about this is this particular implementation we're looking at with FutureTask uses features or limits itself to features that were only available prior to Java 8. With Java 8, this semantic we're talking about got baked into concurrent hash map with the compute-if-absent method. But compute-if-absent, which is this atomic check then conditionally act method, was in fact not available prior to Java 8. So we're going to use FutureTask, which was available prior to Java 8, in order to implement the same semantics that you would now get with concurrent hash map in Java 8 and beyond. So what could happen here is if multiple threads were to come through at exactly the same time, for example, on a multi-core platform, all call get on exactly the same non-existent key, in other words, hadn't been put into the map yet, they would all get back a future that would be null. Because if you recall what happens with a map when you call get on a key that doesn't exist, you get a null back. So we could have, let's say we had 4 threads all calling get on the same key. They would all get back 4 null values. So if you get back a null value, then you've got to do some other work. And what you do in that case is if you're a thread and you call get and you get back a null future, then you have to go ahead and call the compute value method. And that's where the FutureTask really shines, although it's also going to be used in the next method called get future value as well. So keep in mind again that multiple threads could simultaneously call compute value for the same non-existent key. Now, we'll take a look at compute value in a second, because that is, again, like I said, where the cool stuff happens. However, what happens when you come back from compute value is there's a call to this method. It's a helper method, an accessor method basically called get future value. And what that will do is that will return the value of the future. And if the future is completed, we just get the value and we're done. But if we're in the process of computing the future, in other words, we haven't finished, it's still being computed by one thread asynchronously in the background, we're going to go ahead and block in get future value until the future is done. And that's the magic to make sure that only one thread is going to have to wait doing the computation, and all the other threads will block while they wait for that future to be finished. So another way to look at this is the first thread in won't block. It'll actually do computation, which is what you want because it needs to compute that value. But all the other threads, any other ones that came in at the same time, will block until the first thread finishes its computation. So you can kind of think of this in a sense as an exit barrier. It's not using Java synchronizers and barrier synchronizers that we've been talking about, like cyclic barrier or countdown latch and so on. But it's basically the same kind of idea. All the threads that came in at the same time and tried to get the same non-existent key will block except the first one, which will do the computations, and the others are going to wait until those computations are finished. So how does that work, and how does FutureTask figure into this? Well, let's take a look at the compute value method to see what it does. What it's going to do is it's going to compute the value that's associated with the key, and it will return a future task that's associated with it. And of course, that future task is an implementation of future. So the method actually returns a future, but of course, it's returning a future that is actually implemented as a future task using the fundamental properties of object-oriented programming. So down here, what happens is the future tasks constructor, because we're making ourselves a future task now. In fact, we could be making lots of future tasks. The future tasks constructor is going to take in a lambda expression that, when called by the future task in its run method, which we'll look at in a second, will go ahead and apply the function to the key. So what's being passed here is a callable lambda expression that, when called, will go ahead and apply the key and then do the computation and then return the result and basically stash it away. So as you can see here, this callable, this parameter, this lambda expression that's a callable lambda, is going to be called when the code a line or two below calls the run hook method on the future task. But before it can do that, there's a little bit more magic that has to take place. But that's how the callable lambda gets called, is one and only one thread is going to call its run hook method. Well, how does that work? Well, what's going to happen here is we're going to call the put-if-absent method. And put-if-absent was a method that was defined in Java concurrent hash map much earlier on than Java 8. And what it does is it will go ahead and essentially put the item in there if it's absent. And so it's got some interesting semantics here. So it'll atomically add the future task as a value associated with the key. And it'll store the result in the return value. And the first time it's called, so the first time in, it'll return null because there is nothing in that particular value entry in the concurrent hash map for that key because we haven't put it there yet. So the first time put-if-absent is called, it's going to return null. And the next time it's called, it's just going to go ahead and return the value that was stored there. So that's important. So the first time in, we get back a null. And if you take a look at the code here, you can see if the return value from put-if-absent is null, that means it's the first time in, and that means the value hasn't been computed yet. And therefore, that thread, which is the first thread that comes in, will encounter the null, and it will then go ahead and call the run hook method on the future task. And the run hook method on the future task will then turn around and call the callable lambda that was passed as a parameter, and that will go ahead and perform that long-running computation. So that long-running computation will be performed in a thread, and it'll be the first thread in. And anybody else who came along who called put if absent will get back that future. And so that future will be returned, the one that was placed in there. And this is where that future will come from. So the future task that was returned by the first thread in will have been stashed away inside the underlying concurrent hash map by the call to put if absent. So only the first thread in will go ahead and find null, it'll call run, and then it'll return the future task, which now has, of course, been initialized and finalized in the context of what's stored in that entry for that key in the concurrent hash map. Okay, so lots of things to think about. If the future is not null, that means the value is already in the cache, so we just return it. However, just because you get back a non-null future doesn't mean you can make any progress, because it may not have finished the long-running computation in the first thread to initialize it. So at this point, the get future value method is called. All the threads will call that, and it will block until the computation is done. And here's what get future value does. It's actually a very simple method. As you can see, what it does is it just says future.get. And if we're not the first thread in, and we've gotten to this point, that means we've got to see whether or not the first thread in has finished computing the value of that future task asynchronously. If it is not, which could be the case if it's a long-running computation, then future.get will simply block until the future is done. If it has been computed by that point, or when it is computed, then get can return. And at that point, we know that we've actually got the actual value that was associated with that in the map. So again, by the time the first thread in finishes doing its long-running computation in its run method, which calls the callable lambda method, when it gets to future.get, it'll just return right away because the value has been computed by that point. But all the other threads that potentially got there before it will have to block until it's done finishing its computation. So, that was a lot of things to think about. If you ever have to use FutureTask, you definitely want to come back and rewatch this video. As we'll see, the need for FutureTask for things like this have been basically eliminated or minimized with later versions of Java, because this semantic is now baked into concurrent hash map with its compute if absent method. But if you're stuck with earlier versions of Java, knowing how this works could be very helpful.